Okay, welcome everybody to the next session. I guess the speaker doesn't need much introduction. You've probably already seen him last year or the year before or the year before that. For those who haven't, this is Dan Kaminsky. As you can see on the slide, he's the director of penetration testing at IOActive. And well, he's the guy who gave us SSH over DNS, and he will certainly go to hell for tunneling DNS over SSH over DNS, but maybe he'll tell you later. Okay, enjoy the talk.
All right. If you can get any lights killed on that, that'd be awesome.
Okay.
What's up, guys? So I'm out here. Actually, wait, do I actually need this hand mic? I think I can just use this thing. Rock on. All right. I've got way too much material to go over, so let's start. Yay, Swiss Hotel, screw you, Delta Hotel. You dropped a TV on my laptop. Who am I? Some guy. What are we here to do? Break stuff. I do like the pretty pictures. I just have a particularly peculiar definition of pretty. But before we go into the pretty pictures, how many people here thought we couldn't possibly have any more hideous TCP/IP stunts? I mean, come on. It's 2006. Leave the poor thing alone. No. No. We're going to have some fun here. So, see, the great thing about the future is just when the network works, people are like, damn it, the network's working. Let's break it some more. Our net is fast. Why are you working on making it slower? So you've got all these oligopolies who are like, wow, we can't make money with fast net. Let's make money with slower nets. So they're doing all this weird stuff with network neutrality. Thus, people start coming to me, hey, Dan, can you bust them? I'm like, maybe. So what's the closest tool we have to find a network that's screwing with packets on a per host basis? Well, we've got, who here has ever used Firewalk? Rock. Who here has ever used Traceroute? Much better. Firewalk is Traceroute, but instead of using just random packets, you use some sort of packet that you'd actually want to pass through a firewall. And it's a very simple idea. You send your HTTP request 1 hop, 2 hop, 3 hops, 4 hops. Oh wait, it died on hop 4. But if I send SSH, it dies on hop 7. Maybe there's a firewall between hop 4 and hop 5 that's blocking my HTTP packets. So that's what's going on with that. That's how Firewalk works. Now, Firewalk tells you what gets through. It does not tell you who. You can't Firewalk to find out if some other network has special abilities. Well, this suddenly devolves to a very nice question, which is we've always wanted to know what firewall rules someone has, not just with what they'll pass, but for who they'll pass them for. Was there anything we could possibly do? Well, TCP actually is able to do speed measurement on networks in a very interesting way. You've got all these nodes that are communicating, figuring out how fast they're going to send packets, and they don't actually talk to each other. No. You know how the routers tell them to slow down? They drop their stuff on the floor. It's a very small back channel, but it works. And it works kind of well. And it tells us about other people, other hosts, other IPs on the network. Could we possibly combine this with Firewalk? Well, of course we can. What causes packets to drop? Sending too many packets. What are we going to do? We're going to send too many packets. Rock. We set up 2 channels. One is our primary channel. Whatever we get back from, we're not spoofing our source IP. We're actually getting feedback on this primary channel. But there's a second channel. Another stream of packets, extra traffic on the network causes drops, not necessarily coming from us, could be coming from anybody. But how do we know if it gets all the way through? Because it causes our primary channel to start dropping. Think about this. Think about how this merges with Firewalk. Normally, you don't know which packets, you don't know what other packets are on the network. You don't know what's causing your packets to drop. But in this case, you do know because you're sending the packets. You know exactly what they are. You know exactly what they're composed of. And if by some chance some firewall was blocking those packets before it could get onto that router where it would overload the link and cause packets to drop, well, if it's being firewalled in advance, well, guess what? Now you know. Oh, wait, if I send packets from here, it causes drops. If I send packets from there, no drops. The packets must be getting dropped for some other reason. So you can actually use this to very effectively find hosts that are doing filtering, not just on what, but on who. So I'm calling it scorch marking. Why do I call it scorch marking? Well, routers are burning packets, so I figure maybe a couple that are getting through have some scorch marks. Basic model, you download a file from a site, it sends it to you as fast as possible by TCP, and you just start sending more packets. But not from you, from other people. And if your TCP stream slows down, you know, oh wait, there's no block, it's just normal. But let's say it doesn't. Let's say, you're sending as fast as you can, and then you spoof a bunch of traffic from, I don't know, their internal video provider, and those packets get through great. You're like, oh, those packets are preferred. They're allowed to pass anyway. They don't cause drops to happen. So here are some problems. Having to depend on a client is lame. Wouldn't it be nice if you could just scan the internet for routes that were all messed up? Well, let's think about this for a second. When a client is downloading a file from you, what's it actually doing? What is the fundamental service that this client is providing? Well, this client is just acknowledging your traffic. It's saying, yeah, I got that, and TCP does the rest. Well, by any chance, are there other ways that clients could acknowledge traffic from us? Well, yeah. TCP servers acknowledge traffic. You send them a SYN, they give you a SYN-ACK. DNS servers acknowledge traffic. Routers. Routers will send you ICMP time exceeded messages. When you are running Traceroute, you're saying, I'm sending this packet out 3 hops, and you get an error message. You didn't just get an error message, you got an acknowledgement. It saw what you had to say, and it's saying, oh yeah, I saw that. I'm not routing it any farther, but I saw it. So guess what? You can use all your TCP bandwidth estimation stuff, but you can just bounce it right off of ICMP time exceeded messages. Now, theoretically, these messages are rate limited. Realistically, no. You can pass as many as you want, and you'll get as many errors back as you like. It's actually kind of nice. So you can scan for violations of network neutrality. You can find networks that are blocking and passing IP ranges, but it's not exactly efficient. You really have to have a slow link that you're overloading. Now, before, back in the day, you'd never have a firewall before the slow link. You'd never have a firewall in your ISP path that's preventing you from getting fast networking. Nowadays, we have new situations and thus new tools. There's a bigger problem, though. In order for this method to work, you kind of sort of have to DOS some links. DOSing isn't good. DOSing isn't scalable or, ethical, legal, good stuff. So your potential solution would be to find capped acknowledgers. Now, the rumor is that there are actually boxes that are limiting how many time exceeded messages they'll send you. Without having to overload the CPU, overload the link, it's just they'll only send this many errors per second. Great. Thank you. Now you don't need to overload the link, you just need to fill the buffer. And how is this going to work? Your primary channel is also going to be using time exceeded messages. So your primary channel is requesting time exceeded, your secondary channel is either not getting packets through or it's taking slots from your global list of how many time exceeded messages per second you're willing to send. If you can actually find boxes, say, I don't know, like Linux Linksys boxes that everyone has on their cable modems, if you could possibly find boxes like that, maybe you'd be able to get some progress without, knocking boxes off the net. So that'd be cool. Now, if you have code on the client, there might be some cool things you could do using Windows Media Player. Believe it or not, there's actually more than just DRM in there. It will receive video streams over this great protocol called RTP. And it will receive it unicast, UDP, and it will send back quality metrics. How many packets got through, what the jitter was, what the latency was. And you know where it'll send it? Somewhere else. Thank you. So you just spoof a bunch of traffic from YouTube, spoof a bunch of traffic from MySpace, and say, oh, and can you give me the feedback on how many of those packets got through? Yeah, and that should actually work. But we didn't actually come here to talk about TCP/IP hackery. It's just sort of my thing. Let's talk about SSH, which, crap, that's also sort of my thing. So you gotta love SSHing into hosts, right? You go in, the authenticity of this host cannot be established. Do you recognize 09, A9, B1, 99, A4? What? Am I supposed to do something? Yes, says SSH. You're supposed to recognize it. And if you don't, you're insecure and a bad human being. Yeah, this totally doesn't work. But it's one of those dirty little secrets, right? Well, let's fix it if we can. By the way, hex sucks. I know we all like looking through hex dumps, but seriously, hex sucks. The human brain, not built to deal with that. It's sure as hell not built to deal with that. There are exceptions. I know them by name. I worship them. They scare me. We got to find a better mapping. So, cryptonamonics is a field created specifically because the name sounds awesome. There are 3 classes of memory that cryptographers actually want you as the human to have. Rejection, I've never seen that before. Recognition, it's you and totally not you. And recollection. So he had like a nose this big and like hair, bringing back from the top of your head. Passwords are recollection. Now, all SSH actually needs from you is rejection. What the hell is that? I say what the hell is that, but it's the real thing. Well, the hex domain doesn't work. What else is available? Well, let's restate the problem. Humans do not operate on hexadecimal symbols effectively. Are there any other symbol sets that we can use that the human brain is actually compatible with? And the answer is, well, let's take a look around. There have been some other attempts. One group went ahead and used artwork, computer-generated artwork with some fixed parameters. Another group used human faces that were automatically generated. In both cases, what they did is you would look around and see a bunch. You'd say, okay, her, and then him, and then her. And it actually kind of worked. The brain does have some hardware acceleration for faces. The problem is, believe it or not, some people lose it, actually. It's a form of brain damage. Believe it or not, it does work, but it doesn't work that great because you have very little entropy you can actually represent. If you're given 5 choices of 1 out of 9, you have like a 2 to the 16 chance of, just guessing the right one. Well, that's not enough for what SSH needs. SSH needs 2 to the 160, which is quite a bit more. So we need better than this. Well, here's another domain. I'm calling it the mnemic domain. It's basically names. Humans, we actually do have memory. We don't remember arbitrary bits. We don't remember hex, but we do remember stories. Homer's epics are enormous, and for most of human history, those were oral stories that were passed down from father to son, mother to daughter, and so on. Well, stories do change over time. Basic things stay the same, but there is drift. But what actually doesn't drift too much? We still call the guy Homer. So names are actually fairly stable in stories. We seem to have hardware acceleration for them. So could we map the 160 bits that SSH needs us to accept or reject, could we map them to names? Well, let's take 512 male names, 9 bits, 1,024 female names, 10 bits, more variability in female names, quite a bit actually. 8,192 last names. That's 13 bits of information per last name. 9 plus 10 plus 13 is 32. With 5 couples, you can actually represent a 160-bit key. It ends up looking like this. Julio. Now, you might say, but how would I ever recognize these names? I actually went for 6 months logging into every host that I use using these names. Believe it or not, you actually start recognizing them. It's certainly not hex. Now, it is critical. Every time you log in, you see these names. You know why you forget names, by the way? Because someone says, hi, I'm Bob, blah, 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 blah. Like, what? Huh? So it's really all about being constantly exposed. Then the brain's able to actually finally pick it up. And remember, you don't need to repeat it back or anything. You just need to see it and be like, oh yeah, him. Like, wait, that's not Jane. That's someone else, but certainly not Jane. That's all SSH needs from you. This actually seems to work, which, is a nice thing, actually. Now, SSH does have another system called Bubble Babble, which attempts to wrap, and it actually got brought up here. Someone asked me about it. it attempts to map names to syllabic sequences, like Zigaz, Tosus, Vusik, Masar, whatever. The problem is we're not really built to remember arbitrary sequences of syllables either. That's just not what we do. However, gotta actually admit, names are fairly arbitrary. You know, Boutros Ghali is a fairly arbitrary name. Maybe we can merge the approaches. You know, Zigos and Tosik Visuk, you know, Masar and Civic Siled. It might work. I think it requires testing, but we'll see. I'm actually going to try to get some tests done. So, we could actually invert the flow. Check this out. How many people here have passwords that suck? They're like, lowercase hell, $3, tilde, like, you actually speak this thing out like that one up there, that's 23 syllables. What if you just type Dirk and Kuk Kolapajlo and Omar and Gina Heimel? A, you actually get more entropy, 64 instead of 48 bits. B, it's less syllables to communicate, sounds better on a phone, and oh, by the way, how nice would it be to have spell check for your password? I'm just saying. So I'm actually working on this too, and that would actually be dear God, that would save me some annoyance. So I'm working on this, I call them passnims. So it's easier to interface with systems when symbols align. You know, hacking is just another form of interfacing. So we're going to move on to the next section of this talk, which talks about fuzzing. You know, we can really break stuff with garbage syllables. It's depressing. You like take some file, you flip like 10% of the bits randomly, and you know, everything blows up. It's a lot easier than code review. It sucks. So it's very dumb though. You only end up catching small little chunks. Now we can break things way more than dumb fuzzing, which already breaks too much, if we actually, you know what the hell we're doing. That's what we would call smart fuzzing. We take a file, we understand its internal structure, we fuzz that structure, which we understand, and we see what happens. Someone was showing me a really cool PHP fuzzer earlier. Dumb fuzzing is really easy. Smart fuzzing is very labor intensive. It requires like smart people and like specifications. Well, wouldn't it be nice if we could automatically discover what symbols a computer parser was trying to see, to understand? Well, bioinformats are languages. Who here took like a linguistics class ever, studied some language design? Okay, guys, seriously, language is fun. I know it's shocking, but it really is. You know, kids don't actually get the docs to English. I wouldn't want to see them if they were written. Kids don't get the documentation. They just like pick them up just by watching lots and lots and lots of samples. Now they can do this because they actually design all sorts of internal structure and redundancy into the language. And I mean they as in the kids. Children are the actual progenitors of language. They actually create it. Adults, two cultures merge, and they just sort of like, oh crap, we've got to talk to each other, and they make this horribly sounding stuff called a pidgin language. It's like a working language. And then the kids hear and go, oh God, this is terrible, and then they do something good. Well, children make languages, adults make working languages, programmers make barely working languages. Like, well, hell, no one actually has to read this, so we can just go buck wild. And they do. But they are still quite a bit of internal redundancy to these languages. Let's see if we can auto-discover the redundant content. So, there's this great piece of code called Sequitur. It's a linear time pattern finder. It creates what are called context-free grammars from arbitrary input. And when I mean arbitrary input, it's linear time. You can pass hundreds of megs of data into this thing. It'll be like pattern, 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 and it won't slow down no matter how much you throw at it. This is cool. Anyone here ever find a really cool and awesome algorithm and go, wait a second, if I give it more than like 100 things, I'm going to be here all day. Sequitur's linear time. Basic thing that it ends up doing, it would take the input C of, switch C, case 1 value 2, case 2 value 3, case 3 value 4. It's like a compression algorithm. It figures out, case is a symbol and value is a symbol. So I'm going to turn those into A and B. And now my message is going to be switch C, A1, B2, A2, B3, A3, B4, A4, B5. This was created by Craig Neville Manning as his PhD thesis like a decade ago, and he's kind of sort of the chief research scientist at Google. I guess I'll do the evil. So one of the things I started doing, because hex really does suck. It sucks so bad that like fixing it, there's a really low bar. Anything is better. What I did is I said, to reconstruct this message right here, you have to go a certain number of hops in and into the grammar. Like for case and value, you have to get out of S and go one level into A. And A could have B and B could have C, and then C you might have to go another level, another level. Well, how many levels do you have to go to reconstruct each byte? I figured I'd draw it, see what it looks like, visualize it. And what I ended up finding, you can't at all see it in this view, but you see I've given this talk, at least this thing before, so I've seen that it wasn't visible. Much better. Sequitur's finding the internal structure. These are actually hex bytes that I blurred and zoomed in. And immediately, you run this code, and Sequitur's like, oh, here's all the patterns. Let's look at what it's actually finding. I actually went into the output of Sequitur and figured out what symbols it was finding. And it's like, hey, look, we got symbol 84, literal D6. Symbol 84, literal EE. Symbol 84, OC. Now we're on symbol 85, 28. Repeated sequence, single byte literal. Repeated sequence, single byte literal. This is just extracted from the data. There is no like manual operation of, oh, I see this, I see that. No, it just showed up. My goal here is to build better first knives for going after new protocols, and that's pretty cool because I wouldn't want to have to come up with that off the top of my head. And I think there's actually a fixed distance between some of these, like A6, B6, CC, and so on. So we can get even more fun here for various definitions of fun. Let's start drawing links in between the symbols as they are expressed. Now, let's say we just took letters. S leads to W, W leads to I leads to T, T leads to C. That's just going to be a mess. You're going to have like the T leading to the C in switch and like the space leading to the C in case. And it's just going to be a big meaningless mess that has no bearing on what a C compiler parser is trying to do. It's carbonated? Okay. But now, let's look what happens when we actually draw together all the symbol flow with Sequitur. Switch C leads to case, which either leads to 1, 2, 3, or 4, which always leads back to value, which either leads back to 2, 3, 4, in which case it will always go back to case, or value is going to go to 5, in which case it terminates the call. That is actually an accurate view of what the parser's up to. And this is completely extracted from nothing but samples of the data. That's cool. That's a completely new domain that we can go mess with, because we can totally fuzz that. So I built a new tool. It's called the CFG 9000. All right. Time's right now? All right, cool. Rock. It reduces input data into a stream of symbols. And now once we got symbols, let's go fuzz those. Just like we were going to do with bytes with a dumb fuzzer. We can shuffle them around, we can drop them, we can repeat them, we can corrupt the symbols, but do it in a way that is consistent. Every instance of this symbol is broken. Rock! Now, Sequitur is not necessarily the best way to generate a grammar. Doesn't handle recursion, which, by the way, this is hugely used in bioinformatics. And the genome is, now that's a language, dear God. There's another approach called Suffix Trees that may yield better output, but Sequitur scales, like a lot. Like everything else is not linear. Sequitur will take gigs and like just sort of take up all your memory. So some sample output. I ran it on, I had Sequitur fuzz itself, and it's like calculate rule usage. Oh wait, this is a symbol. Calculate rule usage, and so on. I ran this on HTML, and we actually got valid HTML, sort of, and certainly more meaningful symbols than if I had just flipped arbitrary bits. And here's another example. I'm not sure what it's doing, but the browser took it. Now, this is not the best context-free grammar fuzzing ever. Great quote. Many physicists would agree that had it not been for congestion control, the evaluation of web browsers might never have occurred. In fact, few hackers worldwide would disagree with the essential unification of voice over IP and public-private key pair. In order to solve this riddle, we confirmed that SMPs can be made stochastic, cacheable, and interposable. This means nothing. But it got accepted as a paper at a conference. Context-free grammars are pretty cool. They basically fuzz the con and won. So what my goal is to be able to create something that could just look at a whole bunch of papers or look at a whole bunch of JPEGs or look at a whole bunch of things and create something that is semantically meaningless and in fact broken and corrupt. But at first glance, maybe even at 10th glance, hey, that's valid. Sure. Why would physicists disagree? And we'll skip this slide, actually. So I've been working on an updated version of Sequitur called Requitur, which is optimized for fuzzer use, generates larger symbols, eliminates redundant symbols, maybe remove the in-memory grammar requirements so we can scale up to, tens of gigs, grab all symbols from your hard drive, and, add foreign grammar capabilities so you can start analyzing files relative to everything else. But what do I got now? Oh, by the way, code release, ho ho kiddo, 2006. All this stuff is actually, it's crap, it's out. And yeah, if you're trying to figure out how to use it, please send me an email. Maybe I'll figure it out by the time I get it. So Requitur is actually 8-bit clean, which Sequitur isn't. You can't really use Sequitur to analyze raw binaries. Sequitur's been fixed to make that happen. And I created something called merge.dot that actually outputs the graphs that I showed you earlier. So how to think of Sequitur? This is what I want you guys, because there's so much awesome work that can be done here now that we have a symbol level view of all the data we ever look at. Instead of thinking about bytes, think of arbitrary symbols that can be any length, but they're just units. Every time you're thinking, oh, let's look at trigrams, think, instead of bytes, symbols. Instead of Bayesian probabilities for characters, I wonder which character follows which character. Think what symbol follows what other symbol, because that's going to give you the actual flows through the applications that you're trying to break. If you adapt yourself to more than 256 codes per symbol, you're going to be well rewarded for the effort. And if your code's already Unicode aware, you might already be one step ahead. So, symbol analysis systems do kind of have a problem. Languages, kind of like synonyms and more than one way to say it kind of deals. And very similar messages can be encapsulated in very different ways. Very similar messages can be encapsulated in almost identical ways, but they'll still show up as different symbols because the raw bytes are different. This is actually a fundamental weakness of Sequitur. It's looking for exact matches. We need ways of fuzzily linking together our grammars. Now, there are some things we can do by taking all of the entities that our grammar generators come up with and saying which symbols are really close to each other, and then starting to do fuzzing where you do, fuzzy match fuzzing. Somehow that works. I'm going to replace this with a symbol that is similar but non-identical. That sort of stuff. That could be done. But we need to have ways of analyzing, perhaps visualizing, similar but unequal systems. Because the things we're trying to break have a lot of similar but unequal properties. So there's another approach. It's called dot plots. Dot plots are cool. They're pretty. A popular mechanism for visual analysis of human genome, of genetic data. Now, there have been some attempts to apply dot plots outside the domain of bioinformatics. Fair amount of textual analysis, actually some audio, which is how I had heard of it. One of my hobbies is actually audio compression. And there was this really cool old paper called Visualizing Music and Audio Using Self-Similarity. And what it did is it split a song into these little tiny chunks, and it said, I'm going to take each chunk and tell you if it sounds like each other chunk. And I'm going to put it all on a graph. And there's actually a tool you can get from Linux called Disassociated Studio that'll do this for you. And this is actually a Beatles track that they did. And they showed, hey, look. This section right here has this one pattern. This section looks visually different. That section looks visually different. That section looks visually different. As they went through the various segments of the song, very different visual patterns actually erupted from the data. Cool. What if we do this on an MPEG? Way better data. Whoa. That was pretty much my reaction when I was first playing with dot plots. Like, wait a second, this actually works? But yeah, you actually end up getting way more data about what's going on inside a file. So what exactly is going on here? Jonathan Hellman wrote this great paper called Dot Plot Patterns, a literal look at pattern languages. And this was his example. Take Shakespeare, to be or not to be. If we put that horizontally, and we put it vertically, and we put a dot whenever the same word is in that particular position, you'll see to, be, or not to be. and there's going to be a vertical, a diagonal line. Well, 2b is repeated. So we have another diagonal over there, another diagonal over there. Okay, now let's say instead of to be or not to be, we took, say, 32 bytes from a file. And instead of this 32 bytes in a file is the same as this 32 bytes file in a file, or this 32 bytes is different than this one, we actually make it kind of fuzzy. We can use something called the Levenshtein string distance to tell us how similar or how different on a scale from 0.0 to 1.0, how different or similar are these two values. What kind of patterns do we get now? We get some weird stuff showing up. Like file formats really just, these are languages, these are tongues. And, you know, hex is meaningless. But this stuff isn't. Now, understanding these patterns is really hard. In the paper, they describe various things that might show up. Like if you have a stream of messages, A, B, C, D, E, F, G, I, and then all of a sudden it goes backwards, I, H, G, F, E, D, C, B, A, you're going to get like this big X thing that shows up. Or you might get these squares that show up. Or you might get breaks that show up. But I mean, no one knows, no one has ever expected this type of complexity because, you know, this stuff was never built for anything that had this many patterns, you know? It was either being used for text, which is surprisingly unpatterned, or it was being used on the genome, which is patterned, but in ways that defy human comprehension. So, how can we actually make these pretty pictures useful? Little piece of advice, 98% of visualizations are totally useless. The cool part is trying to get to that 2% that it actually can be used for something. So let's figure out what kind of things, questions we can ask that might determine, is there a reason we should do this? Well, the two things we can try to do are A, identify formats blindly, and B, guide a fuzzer. Let's start with the first. Question 1, do different files actually appear different? And does the appearance reflect the existence of internal structure? If we just saw like noise no matter what, this wouldn't be helpful. Well, here's a Java class file. Here's a .NET assembly. CNN's homepage. Packets. Note, we can actually see packet starting, packet starting, packet starting. We can actually see where one packet stops and another begins. Imagine how hard it would be to analyze a packet dump if you didn't actually know where they start and stop. Well, in files, you have that all the time. An individual file format contains all these little tiny chunks, and you don't know where one starts and another begins. Packet dump's a great example of it. With no knowledge of libpcap, I can still tell you when they begin and end. Kernel 32, chromosomes. Like I told you, this was a genetics hack. The Legend of Zelda. So yeah, I think we win that front. But now, do different instances of the same file format appear similar? Text. If you actually take books from Project Gutenberg, text actually isn't very patterned. Now, you'd think it would be, because, you know, English is fairly low entropy, it's 1.3 bits per character, but, you know, you don't usually open a book and the same paragraph is in chapter 1 as in chapter 3. You don't usually see the same paragraph repeated over and over and over again. And so you actually don't get much self-similarity. The symbol clusters don't really align. But law is not text. Holy crap, code is code. No, seriously, like, code does not look anything like any book you would ever see. Like, legal code is very much, we want to say the same things in same ways so we are very clear we mean the exact same message. Legalese is something else entirely, and it straight up shows up in the data. Warning, do not fuzz the law. Or your genome for that matter. HTML. Now this is really interesting. If you look at HTML, it actually has a lot of internal redundancy. First of all, tags. Tags are constantly being repeated over and over again, and thus you get these very small scale repeats. You also get larger clusters because most websites now are built with templating engines. And so constantly looping over, repeating the same expression of a message. And this shows up, and you see this on pretty much no matter what website you go to. You can be like, oh yeah, that kind of looks like HTML. So that's kind of cool. Java class files. Now these aren't as consistent. Now binary code tends to be the most complex thing that you'll analyze. Excuse me. That still has a visible, very deep structure to it. The interesting thing is you are very dependent not just on the compiler. At the end of the day, a file format is a shell for content. And content varies pretty heavily, especially inside of code. This was actually a class factory, and this class factory looked like nothing else I'd ever seen. I have no idea why it looks so different. But clearly, you can have quite a bit of variability that comes not at the format layer, not at the compiler layer, but actually what the heck is the code trying to do. x86 is actually pretty consistent in sections. It tends not to be handwritten. There are exceptions in this room. So as such, complex instructions are emitted in a pretty regularized form. There is an exception. Someone said, you should totally grab like some really tight hand-coded assembly. And I'm, of course, demo scene. Awesome. So I grab a 64K demo, and I grab it, and you know how you don't see anything there? Well, that's because it's just a big mass of gray. You know what compression does? Takes all those nice patterns that you were looking at and just sort of gets rid of them. So you've got this little tiny block of like x86 at the beginning, and yeah, the rest of it's just like unpacker stuff. So you can pretty quickly see packed code. Nintendo games. Gotta love the Nintendo games. So these things actually look really familiar. Like if you actually compare them visually to one another, they have this very blocky pattern. But Mario looks totally different. I don't know what the hell they're doing. Again, output's highly dependent on the compiler and highly dependent on the actual content. I actually think they're doing some kind of packing here, personally. So, do different instances of the same file format appear similar? Well, they can. Similar content certainly looks like itself. But remember, you're measuring the content. You're not necessarily measuring the file format. So, final question. Does one format embedded in another make itself apparent? Well, this is actually kernel 32. And these are 3 different sections of the same file. What's going on here? Well, let's actually take a look at a large file. And I have no idea if this is going to work. And I'm absolutely sure I don't have time to do it, but that's never stopped me before. Maybe. So the great thing about hacking graphically is you end up with like these images that are 1,000 pixels wide and 138,000 pixels tall. Yes. All right, so check this out. This is shell32.dll. This file's 8 megs and is an ungodly mess. Awesome. So check this out. We're just going to browse through it real quick. Oh, wait. Interesting section. Oh, this is all x86 stuff. This is actually a new rendering mode that I created because I needed something that was vertical. Oh, interesting section. What the hell just happened here? What in God's name are they embedding in here? Wait, what was that? Was that a big vertical line? Repeats. So the way this mode actually works, this is actually cool. We're still going through our file. As we go down, each pixel, that's 32 bytes in. So if it's 100,000 pixels down, that's 3.2 million bytes in. So you have this thing right here, but as you go horizontally, you're looking backwards in bytes. So you have to, if you go 32 bytes, if you go 500 pixels to the right, that means you went 500 times 32 bytes back in the file. And so you can see there's repeats at that offset off. And we can just go through this entire thing and start seeing all the various internal structure that this one particular file is containing. Now, I'm not saying this is perfect, but it is If I showed you a hex dump, would you even see differences? I don't think so. So, complain all you want. Hex sucks. So, multiple distinct sections are clearly visible in a way that hex cannot show. Awesome. Now, fuzzer guidance. This is where we actually start breaking stuff. Can we actually locate byte offsets where one section ends and another begins? Well, why would we want to do that? Fuzzers break parsers. There are two kinds of parsers in the world. There are those that were fuzzed during development and those that die really quickly. So, fuzzers break parsers. But there are many subformats to a format, and there are many subparsers to, an actual file format parser. There's all these little paths that you'd want to go after. To a rough level of approximation, when you fuzz a subformat, you fuzz that parser and that parser alone. You want to fuzz one chunk of the file at a time. So if we can split the file up into clearly different, chunks that are clearly different languages, we can go ahead and we can fuzz all these internal chunks separately. We turn it from a problem where you have to, multiply out all the potential changes that you'd have to make into one where you add them out. I fuzz this section, this section, this section. So it's like code coverage. So can we actually locate these byte offsets? Well, very simple math. I alluded to it earlier. You take your file and you just go, let's grab a pixel. This is on the absolute version, not the tilt shift. Well, let's see. We're going to go, this is interesting, this block here. It's at 507 by 507. Well, 507 times 32. The interesting section starts 16,000 bytes in. Oh, look, this square is 570 pixels across. All right, 570 times 32. The interesting section is 18,240 bytes long. Let's get some external verification here. Let's see what the heck this data actually is. We're going to go ahead and we're going to look just a little bit before 16224. We're going to look at 16100. And what we actually see is a bunch of stuff that's like 0381, 0382, 0383, whatever that is. And then all of a sudden, right here on hex 60, totally new format. Totally new parser is going to be reading that. This is actually API calls in kernel 32. So you could potentially find this via hex dump in this particular example. But I argue it was a heck of a lot easier to go, whoa, something happened there. So the goal is use hardcore, which is the name of the tool that I have, as a first knife for locating interesting regions of a file to fuzz. We have a compressed data file here, a video file. And it's 4 instances of related formats. And it's actually really cool. What section should you go after to fuzz? Now, video formats, they're compressed, but they tend to have headers. Well, how do you find these headers? Well, it's very nice to just look at the file and go, done, fuzz that, fuzz that, fuzz that, fuzz that, and just like pick it, grab the offset and go, rather than look through the hex dump, look for something that has an odd number of nulls, look at, just visually take it as hex. I think this is a lot faster. We've got millions of years of evolution giving us a third of our brain for visual processing. Can't we possibly break something with that? So, can we visualize and compare fuzzer operations via dot plots? Well, a major use of dot plots in bioinformatics is actually to compare one genome against another. Thus far, what I've shown you is autocorrelation. That's where you take a file and you compare it against itself. We can actually do something much more interesting, and that would be cross-correlation. That's when you compare a file to a different file. Now, most of the time, this yields crap. However, suppose you're looking at 2 versions of the same file. One from before a patch, one from after. It turns out, most of the time, most things stay the same. Just little tiny things happen to differ. We can see it. Before, we had that line of equality. And actually, it's going to be kind of hard to see, but hopefully you'll be able to see it a little. Before, we had this line of equality, to be or not to be. No matter what those words were, we would always have the first byte's always equal, the first word's always equal to the first word. The second word is always equal to the second word, and so on. Well, now that's not the case, because now we have 2 different versions, 2 different texts, 2 different content. And sometimes they're the same, sometimes they're saying to be or not to be. But other times, words have been inserted, other things have been removed. And that's exactly what we have in this situation. If you actually look, and I know it's hard to see, and I apologize for that, you have a line, formerly very diagonal, very strong. Now it just sort of meanders down. Whoa, big shift over to the right. Back down, big shift, goes down. Note, it's going down, not at this 45-degree angle. It's actually steeper. That means more and more things are getting inserted. When you have the line get steeper, stuff's been inserted. When you have the line go horizontal, stuff's been deleted. And you can see it. You can see it quite fast. And various formats and various patches actually have different outputs. And you can actually see this on files on your own machine. If you grab like the Microsoft Visual C runtime, 7.0 versus 7.1, you just see these things, new code that got shoved in. Actually, this is interesting. You see code that's actually been repeated. Who has a laser pointer? Yes, do that more. How many times do you go to a talk and hear that? But yeah, why might you be seeing, look at this thing right here where you have a second line horizontally aligned. There's code repeated. Cool. So you can actually use this to do diffing. So one of the things I did, and I have to apologize, I have video, but I kind of sort of don't have Xvid drivers on this laptop, so I can't show it. What do you think happens if, I've got these fuzzers, which can also be thought of as really bad patchers. So I've got these fuzzers, and I take my file, and I fuzz it, and I visualize it, and I fuzz it again, and I visualize it again, and I fuzz it again, and I visualize it again. What do you think happens? Well, if I'm actually just using something that's doing single bit flips, my image gets fuzzy from my fuzzer. But if I'm using CFG 9000, which is actually shifting blocks around, shifting symbols, note how with Mangle, which is Ilya Van Sprundel's depressingly effective fuzzer, you still have that sharp diagonal line. With CFG 9000, that thing's just getting thrashed. And you actually get much deeper corruption of your source data. And there will be video on my website later. So, can we visualize and compare fuzzer operations via dot plots? Yeah. Visual fuzzing actually does show differences between files, including the differences introduced by fuzzers. We can see exactly what's going on. The goal at some point is to actually have a fuzzing GUI, Visual Fuzzer 2007. And you'll just see it as an image, be like, that looks cool. You'll highlight it, and that particular block will start turning all fuzzy and changing around. Whenever the code crashes, it'll turn red. So I bet no one thought I could go through 80 slides in under time. Questions? If we actually do have some spare time, I'll just do some stuff off the top of my head. I actually did strip out a fair amount from my other talk. But why don't we do questions on this stuff so far? Anyone? Go ahead. Why don't you go up to the mic, because, or else no one will be able to hear it on the tape.
Are you aware that the diff algorithms, are working exactly like your pictures?
Am I aware that they're, yes, where the picture shows a difference, there's actually a difference. And unlike a normal diff where it becomes a huge mess if it phases in and out of being identical, with this, if it's only a little different, that white dot just gets a little more gray.
Yeah,
you have to have large-scale structural differences in order for the diffs to actually have a visual effect on the similarity break.
As the algorithm works exactly like the pictures, where you're trying to get a path to the picture to find the diffs. Mm-hmm. And the good thing is now you're doing it in your brain, I think, and not on the machine. That's
exactly. Cool. We've got hardware. Let's use it. Go ahead.
The stuff you mentioned early on about scanning for prioritization in routers, have you actually got anything you found via that? Routers that are, or is it theoretical at this stage?
Well, like I said, I can do it. I have the bandwidth. If you have an IP, I have scanned you. I have scanned every IP there. I get the best emails. However, I'm not willing to go ahead and deploy a scan that actually DOSes lines or causes an effect on service, which is why I'm actively looking for things I can scan with that don't take out anything. And that's what I said. Like, when I find something that can do these scans worldwide without actually negatively impacting people's connections, oh yeah. Until then, what I'm probably going to do is deploy some website that you go to and sends you a file, and while it's sending it to you, it's spoofing things from various people. And then it's monitoring the effect on the TCP session. Because at that point, I think I've gotten consent from the endpoint to go ahead and flood them until packets drop. Because that's what TCP would do. I am very careful when I'm scanning the entire internet. Believe you me. Any other questions? So maybe I'll talk about why I'm going to hell. All right, so check it out, right? It's a few years back. It's my first talk, and I go ahead and I present on dynamic forwarding in OpenSSH. This basically lets you do SSH into a host. You can use it as like a VPN concentrator. So if you have SSH access somewhere, great. You can surf the web, move your instant messaging, do all these great things. But there's a problem. When you're doing all these great things, you're still doing your DNS lookups locally. So if you've got some bad guy on your local network, and you're trying to get out of your local network because you don't trust your local network, I can't imagine why that would be the case here. You may be going out, your TCP sessions may be starting from some foreign, safe, wonderful land, but the location you're going to is under the control of the local bad guys. That's not good. So we got SSH patched so that it would accept names instead of just numbers, but the web browsers kind of sort of, Mozilla will do it if you pass it some secret flags, and IE not so much. So the problem is this hole has been around, and if you really don't trust your local LAN, you can't use SSH like this. So I've been trying to deal with this. And I actually finally did figure out a way. So SSH does not move UDP sessions, and DNS normally goes over UDP. SSH, by the way, can forward all these types of connections. It can move web, it can move IM. It can't normally move DNS over UDP because it doesn't understand UDP. But DNS doesn't have to go out over UDP. It could go out over TCP. If you just tell it, no, why don't you try again in TCP? Holy crap, it'll actually do it. So I made a stupid little name server that runs locally that you use as your name server, and you say, every time your machine tries to do a lookup, you go, no. Don't do it locally, don't do it here, don't do it over UDP. Why don't you retry over TCP? And then, bam, SSH can forward it. SSH can forward your DNS. This is not yet why I'm going to hell. 2 years ago, I implemented SSH over DNS. So you could do your web surfing over DNS and your instant messaging over DNS, and it used this same functionality. Well, what happens if we combine, SSH over DNS, DNS over SSH? You actually end up with DNS over DNS. I'm so going to hell. Malkovich. One last thing, just a piece of advice. I did a huge SSL scan. If perhaps you are building a honeypot, you might not want to put an SSL search on the honeypot that is honeypot.yourcompany.com. Now, I was looking at my data, and I thought there was just one company that did it in Japan. Oh, no, there was two. And they're in Berlin. I am so giving them a call. Can I speak to your IT admin? Anyway, we have any more questions? All right, guys, track me down later. Thank you so much.